Sweet. We are live. Okay, I think everything's going good here. I noticed the past two live streams, the audio was kind of fucked up, so I think this is better here now. I had to like crank up my input here immensely. Okay, so I guess we're going over day 2 for calculus. I had a cool experience earlier today. So in learning, I was actually, while I was reading this book, Designing Data Intensive Applications, there is a concept called linearizability. And it is the notion that when you have a distributed database and you interact with it, the database is linearizable if the distributed database acts as if it were one database. So when a transaction occurs, like say I update someone's name from McKay to Billy, then if it's read after the transaction completes, it's immediately available on every single node after the transaction occurs. And the idea of linearizability was like I recalled it, but the idea was sort of floating in my mind and didn't really have a great home. So there's something that I like to think of as sort of hooks, where if you have an idea that you already know really well, sometimes you can hook another idea to it according to the relationship between those two ideas. So this, in this context, there's another thing within, I guess, the area of software engineering, programming, IT, whatever, called DNS. And this is the lookup between IP addresses, which is a sort of a computer assigned ID, you could call it, for networking, and the domain name. So youtube.com would be an example of the domain name. And the IP address would be, I think a series of 5 numbers separated by 4 dots. Anyway, so DNS, it's not linearizable. So when you update a DNS record, which is, you can think of it as just that mapping between an IP address, which is a network ID of sorts, and a domain name, which is the human readable name you see when you type in the URL. It takes a while for those things to propagate. And so when you interact with it, it's non-linearizable. And so I was able to attach this idea of linearizability to something that I understand fairly well, DNS. And now, whenever I think of linearizability, like the concept is quick to come to my mind because I've hooked on to it. So that was something exciting today. But today we are going to go over calculus. So where we left off, I was sort of planning out what my strategy was going to be for, attacking this subject. I think we're going to be watching a video. I guess I think we will be watching a video. And let's see, I'm going to just get my... Yeah, we'll be watching an sort of an introductory video on calculus that should help me sort of get an idea of the landscape of calculus before I dive in. I'm wanting to be sort of as efficient as I can be. And also going forward, I will be reviewing my Anki or using my spaced repetition cards prior to going in and diving and learning more, that will be the initial thing. I've decided to make a separate deck because I don't want to feel... I'm not always great with Anki. I did do like 70 cards today, but I still have more to go. And so I want to be sure that not only are you guys aware of like the entire learning process that is gone through in order to, broach a topic like calculus. But also I want it to be the case that if I don't do my Anki, then I guess in doing my Anki, I don't want you guys this experience to be bogged down by all the other cards I have. That's probably the more important reason there. Because I'd like this to be like, an exercise in learning. I think in things like lifting weights and exercise, that we have a lot of memes surrounding what it's like to lift weights, memes surrounding if you want to get serious about it, you have to do, dieting, hit your protein targets. And then we also have like ideas surrounding, what the correct protocols are for lifting weights, right? And like progressive overload and concepts like these. But we don't have a lot. And then additionally, videos are really good ways to present like fitness topics, right? Because you can see it. Additionally, like I think I mentioned this in the very first stream I did, but like learning is sort of a hidden activity. Like you could have like an array of students in the class, and they could each be having distinctly different learning experiences, and like ultimately are, and those learning experiences have different outcomes. And so I'd like this to not only be an investigation on like what is most efficient for learning for me, but also to be like an expression for, like a video expression of like the fact that I like learning, and also to teach these sort of things that aren't taught at all, that are mostly implicit, and you just kind of like have to like limp along until you figure it out. So I think we'll go ahead and start. I think I'd like to start with a broad overview. My sort of approach from this outset is I wanted to pull out from my memory all the ideas that I knew about calculus before, which were, relatively little, and then get an idea for the overview of calculus. What is calculus generally? And then I'm wanting to split things for like learned calculus. I want to split things between concepts understood and procedures like able to do, if that makes sense. So I'll be going over what you could think about as like procedural memory, or the act of doing calculus, and conceptual memory, or the act of understanding calculus. And I'll separate those because I think that's a good division. For someone who knows calculus, they know how to do those two things. And then also separating them out like that can help you more focus on exactly what you don't understand. And so I think that will also be beneficial. Because if I'm having like a great time conceptually, but procedurally I'm having issues, it's like silly to focus more on the conceptual stuff. You want to focus on what's most important, right? And so, yeah. So with that, I think we will go on in. I do want to triple D check that we're okay. Yeah. We are looking good. I think I'll just keep that live up so I can see. Okay, perfect. So I didn't write much more down before going into this, but I think that is quite all right. Perfect. So I think we're just going to watch this video I have pulled up. And then after we watch the video, I'll kind of like figure out. This is sort of for us to be able to get the lay of the land for calculus. And then I will be looking through these as well. We did have some like seemingly good content here that we pulled from ChatGPT. Okay, so I think I'm gonna do this 2x speed.
Areas of calculus that...
And we were muted, so there we are.
In this video, I'm going to attempt to teach the fundamentals of calculus in a very short time. So there's 3 areas of calculus that you want to be familiar with. The first one is limits. Now, limits help you to evaluate a function. Let's say if we want to evaluate f when x is equal to 2, but for some reason the function is undefined or we just can't do it. Well, a limit will allow you to see what happens as x approaches 2. And so limits are very useful to find out what happens to a function as we approach a certain value. Now, the second area of calculus that you want to know is derivatives. So what are derivatives? Well, basically, derivatives are functions that give you the slope of an original function at some value. So let's say if I have some function f of x. The derivative of f of x is known as f prime of x. Now, this function here...
Okay. So I'm just kind of listening in to figure out what these are. So he did talk about the nature of derivatives. We'll just get that term again.
If I have some function f of x are functions. So what are derivatives? Well, basically, derivatives are functions that give you the slope of an original function at some value.
Okay. So these are functions that give you the slope of a function at some value. Functions that give you a slope of a function at some value. Okay. So that's not entirely clear to me. It's a little opaque, so we're just going to dive into it a bit. Okay, so if derivatives are functions, and it gives you the slope of a function at some value, unless he's not being precise with his words here, it seems that derivatives are functions that take functions. Well, so I guess the inputs to a derivative would be the function we're deriving, and we'll just call this just parts of a derivative. Oh. So we have inputs to a derivative and outputs to a derivative. And we'll just call those inputs and outputs. And I think I might zoom in here. Doop. If I can. Okay. I think that's better. Maybe one more. Okay. So for the inputs for a derivative, we have the function we're deriving, and then we are giving some value, and then we have the slope of the function being derived. Okay, I feel good about that. Okay, so functions that give you the slope of a function at some value. Okay. I have heard about this before. So I guess one thing I did right here was, before trying to get more information, I tried to, from that like idea or the definition that I was just given, I tried to pull apart what is the nature of a derivative. And in that, I exerted some mental effort to do so. This can be thought of, or this idea is called, or I guess the idea of exerting mental effort. I talked about this previously, but this idea of cognitive load. So I'm exerting mental effort towards understanding this thing. And when we exert mental effort in this way, it is beneficial. So there are desirable difficulties within learning, and this was an example of one. This week I'm going to be spending some time to like get a refresher on the topics within educational psychology, so I can like speak more explicitly and clearly here. Anyway, so we pulled out. So we have inputs for a derivative and outputs for a derivative, and our inputs are of the function we're deriving, the value of the function, and then the output is the slope of the function being derived at a given value. So I have heard about like this idea before, about like how we're like looking at the slope at a particular point. And I want to dive into this just a little bit more. What is it? Excalibur. Okay, so oops. Like in most things, it would be like super easy to figure out like what the slope is, like at given points, right? Because the slope for this line doesn't change at all. Like we'll say, oh, that's really not aligned. We'll redo this. Will be, oh, this one. Okay, so we'll just do 1, 1 here to make it easy. So we'll say here, and it meets here. I was a little ski-wampus. Anyway, so the slope of this line would be 1, because we're rising 1 and running 1. And so, like at any point of this line, the slope is the same. But for like, if we were to do other things like curves, like the slope is different here, is different here, is different here, is different here, is different here. And so I think derivatives are what are going to be helping us do this. Shoop, 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 shoop. Okay. So let's keep going.
So let's say if I have some function f of x. The derivative of f of x is known as f prime of x. Now
okay. That's also another thing. So we just got some knowledge on the syntax for describing derivatives. So f of x what is it? Probably just an apostrophe. Prime of x. And it may seem odd that I'm like sort of stopping so much and pulling out so much before we continue onward. But as I'm interacting with these things, I'm like trying to understand them fundamentally, because like the more effort you exert, or like the closer you get to a good understanding from the outset, the better you're off. So you shouldn't focus on merely like zipping through material, because the end goal of learning isn't just about zipping through material or like flexing on people for how many books you read this year. It's about understanding. And so like there are parts of this video that I'm probably going to be able to move quickly past. And then there's also probably parts that like this that I'll need to go slower. But I'm focusing on all the things that are being described in this, so that I can have a good idea. And so you shouldn't expect that like all things you learn like flow at the same rate.
This function here will tell me the slope of this function at some x value. It will give me the slope of the tangent line. So derivatives are very useful for calculating rates of change. Now the third area is
Okay, there's two things that happened there.
useful for calculating rates of change. So derivatives are it will give me the slope of the tangent line.
The slope of the tangent line. I'm not sure what that is. So we'll just keep this later. What is the slope of the tangent line? Okay. So that's another question. That's a question there. So we'll just kind of stew in that. And as I'm going through, like there are many things you can do, or many approaches you can take to learning, and I'll be experimenting as I go on.
So derivatives are very useful for calculating rates of change. Now the third area is integration. Integration is basically the opposite of derivatives. With integration, you're basically finding the area under the curve. Integration is very useful for calculating how much something accumulates over time. And what you need to know is that derivatives and integration, they're opposite.
Okay, so looks like when I was thinking about calculating the area under the curve, I had heard about that idea in calculus. It was in fact integration that I was talking about. Okay, I'm feeling good about that. So the big parts of calculus are limits. So what happens when I approach a certain value for a function? We'll have to understand that a little bit more. Yeah, probably what happens with the function as I approach a certain value. Derivatives, these are determining the slope at a given point within a function. And then I also have integration, which is purported to be the opposite of derivatives. And this is the idea of calculating area under a curve. Okay. Perfect. So like one thing that I'm thinking about before I go in is that like, and this is a good thing, like to have questions come up like this is good. Because it demonstrates you're engaging with the material, and if you have questions and then they get resolved later, then you'll have like more memory of it because you're exerting effort into trying to fit this thing you're thinking about within the structures of your mind, and some things that don't make sense emerge from that, right? Those are questions, at least as I'm describing here. Okay, so one thing about I guess both, well, okay, I guess I mostly have an issue with derivatives right now. So like, that's not a great bell curve. It's got it looking thick. So we talk about this slope here, and like when I calculate slope normally, I need 2 points. So it's not clear to me, like if we're calculating slope at a point on a curve, and so like from the previous math classes I've taken, like that does not fit well with my understanding of how to calculate slope. I have heard that like you can think of it as calculating at like it has something to do with like infinities. If you were to like look at the finest point of that and then calculate from there. But I guess that this overarching thing is that like my conceptualization for how slopes are calculated, like I have no ability to describe, or I don't understand how we could derive some slope unless we were to just arbitrarily pick like 2 points that were like super duper close to each other but not the same, right? But for this, we're looking at the slope given some value, right here, some value. So that's something I don't understand. For this one here, for our this would be our integrations. I think there is the issue of finding the area under the curve like poses a problem. Like I don't like conceptually, I don't know how we can grab that. Though if we do know like the entire if we do know the entire area under the curve, and we know what proportion of the under area of the curve we're looking for, then it's like a simple problem there where, if we're looking at, 40% of, or the line that we're looking, or let's see, if we were to say that this was 20% of this entire curve here, and we knew the entire amount of the curve, we would just have to, take 1/5 of the total volume underneath the curve to get our little integration area. But I'm not sure how we calculate or like what enables us to like find this value here. Let's see if there's anything else that kind of yeah, so I guess also with limits there is another thing where like it's helping us understand what happens when you approach a certain value, but it seems like we have to make some sort of arbitrary distinction at like what point we're saying, okay, this is the level of approaching that we want. So it seems like there should be a way to specify that. Yeah. So let's just write out these questions. So the question here would be, how do we specify our level of approachness? If that makes sense. Seems like we are going to have to make some arbitrary distinction. Or just choose some value that is industry standard. Okay, and then for derivatives, I'm also going to do opposite of integrals here. So I also don't understand like how these can be considered opposites now. So maybe I'll just put that below. Actually, this is what I'll do. There we are. So how can integrals and derivatives be considered opposites? It seems that slope and volume are pretty distinct. So let's think. So okay, so for derivatives, which are the slope, right? I guess you could, if I were to do derivatives along this entire line here, then I would sort of understand the shape up to that point that we like make that a cutoff, like however that's done. And then I would actually have like a pretty easy shape to like squares are easy to calculate the area for. And so I could see that it could be the case that when we're doing well, let's see. The integration to calculate the area under the curve. that there seems that, like, if they're talking about opposites, it seems like there could be a connection here where we're doing this derivative. If we do the derivative of then this may be just like hogwash, like the way I'm speaking about it. But this is like an exploration, right? And so if we were to do something like the derivative along this, well, that wouldn't be the opposite. Okay, I'll just describe. So we could do something like, or it may be the case that the derivative, rather, it seems like completing a derivative along this slope here would allow us to understand the shape of that slope. And then after we understand the shape of the slope, it seems like a fairly trivial thing to calculate the volume, because that's like the most complex thing. Like if this were just a square, it would be like piece of cake to figure out what the volume is, right? It's this thing here, or the slope here, that makes it difficult. So I wouldn't call integration and derivatives opposites. According to my present understanding, obviously in the video they said it was opposite, so I mean, can't super argue there. And then I'll say, could be that a derivative, yeah, the way I'm describing here doesn't seem like they have the behavior or the relationship of being opposites. Could be derivatives are taken along the slope of the volume of the curve, or along the entire line of the curve under which we are trying to calculate the volume. Okay. Okay. The integration, the idea of it, how it's telling us about how things compound over time, seems pretty reasonable. Like if I were to take a integration for this little triangle here versus this one here, and this was t time, then it makes sense that like I'm taking like little snapshots about how the relationship or how the phenomena of what we're tracking emerges. So I think that seems reasonable to me. Yeah. Okay. Let's continue.
Opposites of each other. For instance, we said that the derivative of the function f of x is equal to f prime of x. That the derivative, they're opposites of each other. For instance, we said that the derivative of the function f of x is equal to f prime of x. So this is the derivative of the original function f.
Okay, so this is new syntax here. So maybe this is another way of saying derivative.
The integral of f prime of x.
Okay. And then looks like we have like a little s guy for integral. Oh, okay, so yeah, he hasn't finished it here, but he's literally defining them as opposites. Okay. Okay. Is the syntax is a little S shape, or I guess it's a big S shape. Okay.
is f of x. So this is
Okay, so I'm still not super understanding how we're able to swap things here. Because here we're using d over d of x, and then f of x equals f prime of x, which is the derivative of f of x. But now we're using f prime of x, or yeah, the derivative. Well, the derivative of the function of x times dx, or maybe this is the way that they're describing. Like dx might just be like a name. Well, no, that like says, oh, I'm a derivative. But also we already have this syntax here, like f prime of x, and so it seems like that would be redundant. Okay.
is the antiderivative, or the integral of f prime. So you can think of
Okay, antiderivative, or the integral of f prime.
of integration as of action relates over the sits of each other. For instance, we said that the derivative of the function f of x is equal to f prime of x. So this is the derivative of the original function f. The integral of f prime of x is f of x. So this is the antiderivative, or the integral of f prime.
Okay, so it seems that rather than being, well, I guess, yeah, okay. So maybe the way that they're opposite is that they're opposite, or so the way that integral and derivatives are opposite are that they are the opposite functions. So if we're doing the s was integral on like f prime of x, and that gives us the antiderivative, or what seems to be our original function. It seems that taking a derivative brought us to f prime, and then taking the integral of f prime brought us back to our original function, or the antiderivative. But it seems odd that, or maybe it's normal, but it seems odd to me just from the outset that the antiderivative would, like you call a normal function an antiderivative. So I'm not sure. So I'd like to get some clarification on this syntax here. And so what I'm just going to do is I'm going to take a quick snip of this. Shoop. And then I'll just put this here. And then I'll also ask a question regarding the opposite nature of integrals and derivatives. Or maybe Okay, so I'm wanting some clarification on the syntax of integrals and derivatives. Does d over dx show that we are going to be doing a derivative? Is it merely like a signpost? Also, what about the symbol for integrals? Is this the same? Also, I'd like to understand a bit about the nature of how integrals and derivatives are opposites. It seems that they are opposing functions, meaning that the derivative of f of x will create something, f prime of x, that can be undone by taking the integral of f prime of x. Is this true? Okay. If not correct. So we'll see what we have here. So this, yeah, so the big idea is this thing is the person describes this as the antiderivative here, where it seems to match exactly, well, yeah, it seems to be what's going on right here. Okay, so it looks like we have, I'm going to just zoom in so it's more clear. Okay. So it looks like d over dx is indeed it's an operator. Okay. So take the derivative with respect to x. Okay. That's totally reasonable. Oh, with respect to x. Okay. So I could plug in a value. Oh, okay, I see. And that's a function of x. Okay. So just had a little bit of an aha. So d over d of x is the notation for taking derivative, and x is the input for the value, or the direct x. The x here is the input. Maybe it's the input, or maybe it's just a sort of like a parameter. So the question I'm asking here is d over d of x. Can I substitute x for 1 and do d over d of 1? Or is that okay? I don't think so, since it describes as an operator, and typically operators are the minus sign, the plus sign, and so it seems like d over d of x is merely an operator that says merely an operator that says, hey, I'm doing this, instead of me being able to replace x for the value I'm going to be passing into the function, such that I get the slope on the as a result of doing the derivative on that function. So if I do the derivative at 0.5, as in not 0.5, but the 0.5, or the value 5, I'll get the slope where the function equals 5, or at least that's my understanding. Okay. Something. So is the x in d over dx something that can be substituted? Or substituted? Or is it just a part of the operator? A part of the operator. Okay. So it looks like it just says, hey, we're taking the derivative of x. Okay. So the response was in d over d of x. The x identifies the variable for a differentiation. It's not a particular placeholder you swap out arbitrarily, but rather specifies which variable the derivative is taking with respect to. But the function itself, but in the function itself, I can replace x for a given number. Correct? I believe this is true. Yes. Okay. Okay. Perfect. Sweet. Okay. So, I think we are going to, like, pause here real quick. Well, yeah, I think it's reasonable to pause here real quick to begin making Anki cards. And we may honestly be, like, at the time at which we, or after we finish making the Anki cards, we might be at time. So, okay. And so, again, this may seem odd that I'm exerting so much effort, it seems, to, like, picking apart exactly what's going on. But I'm seeking understanding, right? And so if integrals and derivatives and limits are, like, really important to calculus, which from, you know, my overview of what I've seen, it seems they are, right? Then it's reasonable to just, like, have those ideas really down well from the outset, you know, like as immediately as you can. Whereas I haven't taken a calculus class before, so I can't tell you this is the case, but I'm sure it's probably likely that many people go through the class still not having a good understanding for what integrals and derivatives are. And obviously, I'm not there yet, but yeah. But okay. So we're at 2:21 of the 36-minute video. Okay, so what is the symbol for integration called? And I don't actually, we'll just Google this because I don't want it to ChatGPT to take forever. Is an elongated S. Okay. I guess it's just called the integrated symbol. Integral sign, or integral symbol, or just integral for short. Okay. Let's see. What does the integral symbol look like? In calculus. Okay. And then I think I'm going to pop open another so in this so I'm going to pop open another chat here. In this chat I've specified that I'd like to have a card and a reverse card. The idea we talked about earlier, where I'm making the connection between a definition, or a term and a definition, and the definition and the term. So it would be, let's see, a prime number, I could ask, you know, what is a prime number, or prime number, and then this is a number that is only divisible by 1 in itself, or whose factors are only 1 in itself. And then I could say, this is a thing or this is a number whose factors are only one in itself, and the answer would be prime number. So on one of them, the question is, what is a prime number? And the other one, the question or statement is, or the front side is, what is a number that, or what is a number that, or what is a number whose factors are one in itself, or who is only divisible by one in itself. And so that's what I've done here. And that helps you connect to the terms, because sometimes you can remember something one way, like a term to a definition, but you can't recall it from a definition to a term. And so this is like a useful tool. So I will just see this and see if they do it well, because what I'd like is to have the integral symbol shown. Oh, you are not doing what I was anticipating you were doing. So I'm just asking if they could follow the same format. Follow the same format you were following previously. Okay, I was having to give some examples because it was like not doing great previously. Oh, boom. But this is perfect right here. Okay, now so we'll add that. What is the derivative operator in calculus? No need to give examples or a summary of what you are doing now. Just follow previous format. Okay. Perfect. Okay, so sometimes it just like totally shits itself here. So I'm asking what the derivative operator here is, and then I'm asking what the derivative operator here is. So sometimes it does not get what is this operator within calculus? Calculus d of x. Okay, so we will go ahead and add that. Sometimes it does good with the reverse card. I probably just need to give better examples, honestly. But yeah. Okay, so now we've done those two things. And I think I want to like bring these into Anki here. What is a derivative in calculus? And so what I'm doing here, so typically I will write the question out and then have ChatGPT or another large language model provide the answer. It is the case that if I were to come up with the answer on my own, that I would remember it more. This is called I believe the generation effect within psychology. But this is sort of I don't know. I'm saving more. I feel like if I do have an understanding of it as of yet, I'm just saving time if I do it. And if you don't have a good understanding, it might be good to come up with the answer because that will enable you to arrive at understanding, or hopefully, right? But yeah, so I typically don't generate my own answers. But when I'm learning something, I just type out the questions. So now we have what is a derivative in calculus. I think I will do another chat here. And I wish that control click worked like a control click instead of not that. And I think I'm just going to do 4.0, but I want the question. Less than. And then when I'm doing it, I typically want around less than 50 words, so I'll specify that. And then I'll say also provide an Anki style reversal. Okay, so this is a different definition than I received earlier. Oh, actually, no. Okay, interesting. So this seems to be correct here. Let's see if it brings over this. No, it does not. Okay, so this will be important later because this seems like to be the function for a derivative, which is new. Okay, so we'll do this here. What is the calculus measure? The measure within calculus. What is the measure within calculus? Or what is the measure in calculus? What is the function in calculus that measures how a function changes as its input changes? In other words, it represents the function's rate of change or slope at any given point. Okay, I think that's reasonable. Doop 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 doop. Okay, what is the limit within calculus? One thing you could do as part of this generation effect is I could answer as I'm asking the question. So it's really only the text generation portion that I'm saving time with adding into ChatGPT. So the limit in calculus is less than 50 words. This is the nature of, or this is the process, or I don't know if it's a process by which, let's see, a limit is the measure of, or rather, the result of a limit is that we are looking at how a function changes as it approaches a threshold or a value. Okay, so maybe a better way of saying that would be a limit is a measure for a function that a limit is an evaluation technique for a function that measures how the function changes as it approaches a certain value. I'm comfortable with that. Oh, interesting. This is new. It forms the foundation for derivatives and integrals. Interesting. Oh, okay. So when I was talking about like this issue here, about like not being able to understand, oh man, I need to. Okay. Okay. About not being able to understand, like how they just arbitrarily pick let's see. So previously I said, okay, my conception of finding a slope is I need 2 points, and then I can do the slope formula, which is like I take this point, it's like y1 over y2, x1 over x2 or whatever, something like that. Anyway, so to find this slope here, and then here, like it seems like we don't do that in calculus. It seems that we're not like selecting these points here, but we're like at a single point. It seems we figure out what the slope is, and so the limit is this point, I believe, or rather, the limit is the approach of selecting the point. So since the limit is how we are looking at how a function is as it approaches a certain value, I'm not 100% sure about my preciseness here. But it seems that limits is like a really important thing here because, and it may be the resolution of not having 2 points here. So maybe calculus is a tool set that enables you to be able to have some capability for specifying the slope, or rather, for getting more information that I think, or for getting more information from a single point, given a function that I thought could that I thought could occur previously. Okay, interesting. Okay, so. So if I just had a point, I could not, I would have zero capability for determining a slope, right? Because I could have it cross through at any direction, right? But for these functions, right? So the function is an incredibly important part of the limit. Obviously, like, it helps you evaluate a function, but the nature of it being a function is what enables me, I think, I think I'm confident in saying that, to be able to then get the slope, because the function, embedded within the function, is maybe a representation, or no, embedded within the function is the nature of, like, I guess this would be the output of a function. So embedded within the function is the nature of all the slopes of a function, or embedded within a function is the form that the outputs take. So this would be the form the outputs take. And it may be that I'm thinking, or maybe... Okay, anyway, so a function describes, or has embedded within it, a function that describes this line here has embedded within it the slopes of all areas of this line, because holistically it has the entire package, right? And so the limit enables you to figure out, I'm thinking, the limit enables you to figure out, okay, given this point, or maybe this slope of the line, what is the, what is the slope at this given point? I believe that's the correct, that's a good connection with a limit. Okay. So another thing that I'm just found myself doing, I think is good, is creating hypotheses about how things are. Because if I create a hypothesis for a particular thing, it makes explicit how I'm thinking about that thing. And if it is the case that when I'm learning something, that I'm trying to get the correct conception of that thing in my mind, then creating hypotheses about how this thing should be in my mind, or what the thing is in itself. So creating a hypothesis about what derivatives and what integrals are, enables me to prove myself wrong and change how I think in my mind. Instead of just having a fuzzy picture of maybe, hopefully I know how it is, putting yourself in situations where you can be proven wrong, is actually really good for understanding. Okay. I seem to have closed out the video. No, I did not. Oh, there it is. Doop. Okay. Perfect. So I think we will call it there for today. I think next, or I guess tomorrow, we're going to be looking at tomorrow we're going to be adding more of these Anki cards. I think we'll be first reviewing them and then adding them. Maybe, I don't know. And then we'll be continuing from the 2:21 point of the video. We only have 34 minutes left. Exactly 34 minutes. Look at that, 21. Sheesh. Okay. I will see you tomorrow.